Hello everyone, welcome back to the Simple Spark YouTube channel. Today we are diving into part 4 of the light chapter, Refraction of Light. Let's get started. Let's start with a really cool effect you have probably seen before. Imagine putting a pencil into a glass of water. It looks bent or broken, right? But it's not the pencil that bent, it's the light that's bending. This bending of light is called refraction. Refraction happens when light passes from one medium to another, like from air into water. Why does it bend? Because light changes speed as it moves through different materials. So, what actually causes refraction? Here is a simple reason. Light changes speed when it travels through different materials or medium. When light enters a new medium like from air to into water, it slows down or speeds up depending on how dense the material is. This change in speed causes the light to change direction, and there's the bending we see. Media can be denser like glass or water, or it can be rarer like air. And depending on whether light is moving into a denser or rarer medium, the direction it bends will be different. Here is a diagram showing two types of refraction, that is light entering a denser medium and light entering a rarer medium. Notice the change in direction in each case. Refraction isn't just some science concept, it's something we see every day. For example, when you put a pencil in water, it looks bent or broken. That's refraction. Another example, drop a coin in a bowl of water and look from the side. It looks raised. That's also refraction at work. And even your glasses or camera lenses bend light using refraction to help you see clearly or focus images. Cool, right? Refraction is happening all around us. You just have to look. Now let's go over some important terms you will see in ray diagrams. First, we have the incident ray. That's the ray of light coming in approaching the surface of the second medium. Then we have the refracted ray. This is the ray that enters the second medium and bends. To help measure all this, we use an imaginary line called the normal. It's a line drawn at 90 degrees to the surface right where the light hits. Now let's talk angles. The angle of incidence marked as I is the angle between the incident ray and the normal. The angle of refraction marked as R is the angle between the refracted ray and the normal. And finally, the type of medium matters. A rarer medium is where light moves faster, like air. A denser medium is where light slows down, like water or glass. As we go through ray diagrams, keep these terms in mind. They help us understand how and why light bends. Let's take a closer look at refraction through a rectangular glass slab. When light enters a transparent glass slab at an angle not straight on, it bends as it enters and then bends again as it exits. Let's break this down with the diagram. First, the light ray hits the first surface of the glass. It bends towards the normal because it's entering a denser medium, glass. Then, as the light travels the glass slab, it moves back into air, which is a rarer medium. So now it bends away from the normal. But here is the cool part. The emergent ray that comes out is parallel to the incident ray, but it's shifted sideways. This sideways shift is called lateral displacement. Let's define a few more important terms here. Emergent ray. This is the ray that exits the glass slab and re-enters the air. Angle of emergence, that is represented by E. That's the angle between the emergent ray and the normal at the point it leaves the slab. Lateral displacement. This is the perpendicular distance between the original incident ray and the final emergent ray. It shows how much the ray has shifted sideways. And optical medium just means any material light can pass through, like air, glass, or water. So, to recap, in a rectangular glass slab, light bends twice towards the normal when it enters, away from the normal when it exits. And even though the emergent ray is parallel to the incident ray, there is a small side shift, that's the lateral displacement. Let's now look at the laws of refraction of light, which explain how and why light bends when it passes from one medium to another. The first law states the incident ray, the refracted ray, and the normal all lie in the same plane at the point where the light hits the interface of two transparent medium. Second law is also known as Snell's law. It says that ratio of the sine of the angle of incidence to the sine of the angle of refraction is always a constant, as long as the color of light and the two media remain the same. This constant is called refractive index of the second medium with respect to the first. It is written as sin I divided by sin r is equal to constant, or sin I by sin r equal to constant, where I is the angle of incidence and r is the angle of refraction. In the diagram, you can clearly see how the light bends as it moves from one medium to another, and how Snell's law helps us predict exactly how much it will bend. So, to summarize, refraction follows two clear laws, one about how all rays lie in the same plane, and one gives us precise mathematical relationship, Snell's law, governed by the refractive index. Let's talk about the refractive index, a very important number in understanding how light behaves. The refractive index tells us how much a medium slows down light as it passes through. A higher refractive index means the light bends more and travels slower in that medium. So the amount of bending of light depends directly on the refractive index of the medium it's moving through. So, the refractive index is the number that tells us how much the light slows down when it goes through a material. Different materials slow light down by different amount. Light travels fastest in air, if refractive index close to 1, so it hardly bends. Light travels slower in water or glass, refractive index greater than 1, so it bends more when entering this material. Let's see some of the formulas for the refractive index. Absolute refractive index. This is used when light travels from vacuum or air into another medium like water, glass, etc. The formula is N is equal to C divided by V, where N is refractive index of the medium. C is the speed of light in vacuum, approximately 3 into 10 to the power 8 meter per second. V is speed of light in the medium. The refractive index is the ratio of how fast light moves in vacuum compared to how fast it moves in the medium. Higher N means light moves slower in the medium. Next one is relative refractive index. Relative refractive index. This is used when light travels from one medium to another. When light travels from medium 1 to medium 2, N21 is equal to V1 by V2, where V1 is speed of light in medium 1, V2 is speed of light in medium 2. N21 is the refractive index of medium 2 with respect to medium 1. When light travels from medium 2 to medium 1, N12 is equal to V2 by V1, where N12 is the refractive index of medium 1 with respect to medium 2. The relative refractive index compares the speed of light in two different media, showing how much light slows down or speeds up when going between them. The higher the refractive index, the slower light travels in that medium. Optical density. Optically denser means the medium has higher refractive index. Optically rarer means the medium has lower refractive index. Optical density is not the same as the mass density. For example, a medium can be optically denser but physically lighter, like kerosene compared to water. Diffraction direction rules. When light travels from an optically rarer medium to an optically denser medium, light slows down. Light bends towards the normal line, the imaginary line perpendicular to the boundary. But when light travels from an optically denser medium to an optically rarer medium, light speeds up. That means light bends away from the normal. We can take the example of kerosene and water. The refractive index of kerosene is 1.44, whereas refractive index of water is 1.33. Even though kerosene is physically lighter, less mass density, it is optically denser because it has higher refractive index. So the refractive index of a substance is measure of how much it slows down light compared to the speed of light in a vacuum. Higher refractive index means light travels slower in that substances and the substance is optically denser. Lower refractive index means light travels faster and the substance is optically rarer. So below there is a table that shows the substances and their refractive index. Air has refractive index close to 1 because light travels almost at the same speed as in vacuum. Water slows light down more than air, that is n equal to 1.33. Materials like diamond have a very high refractive index 2.42, meaning light travels much slower inside diamond compared to air or water. Optical density increases with the refractive index. For example, diamond is optically denser than water or glass. This table helps understand how light behaves in different material. For example, how much light bends, that is refracts when entering or exiting these substances. So, we have learned that Refraction is the bending of the light when it travels from one medium to another due to change in speed. Laws of refraction, that is the incident ray, refracted ray and the normal all lie in the same plane. The ratio sin I by sin r is a constant where I is the angle of incidence, r is the angle of refraction. Refractive index n is equal to c by v, where c is speed of light in vacuum, v is speed of light in the medium. It indicates how much light slows down in a medium. A higher refractive index means more bending of light. Optical density versus mass density. Optical density is not the same as mass density. A medium with higher refractive index is considered optically denser. Glass slab refraction. When light enters a glass slab, it bends towards the normal. When it exits, it bends away from the normal. The emergent ray is parallel to the incident ray, but it is laterally displaced, shifted sideways. That's a wrap for today's topic on refraction. In our next lesson, we shall explore spherical lenses and how they work. Thanks for watching the Simple Spark. If you enjoyed this video, please like and subscribe for more clear and simple science explanation. See you next time.